go on to Unit 2, which is organic chemistry. So we're going to have some fun with organic chemistry. So please, if you can read Unit 2 and take a look at it, and then we're going to talk about it. So here comes Unit 2, organic chemistry. Yes, it's true. Carbonyl is a very good thing to say. There is a carbonyl group here, but please impress me. Don't. Yes, there's a carbonyl group there, but what is the name of the functional group that you see before you? Yes, so that is the carboxylate anion. And before you look at the board, if you also want to impress me, please write the Ka for the equation that is provided in Unit 2. So if you have some paper somewhere, please write the Ka for the equation, the chemical equation that you are provided with. And by the way, if every single one of ACER's practice booklets, all four of them, have questions about Ka, Kb, pKa, pKb. So, I mean, the chances that you will have it on your exam, very, very, very high. So, okay, so here are the main ideas that I want to make sure that you understand. First of all, I would like you to name this compound here. Please name this molecule that's drawn here. What is the name of this molecule? Yes, this molecule. So just to get you oriented, yes, we've got all the right things being said now. So this molecule, just to get you oriented in organic chemistry, whenever you see a corner of a geometric figure, it represents a carbon. So there's a carbon here, and then there's a carbon here. So this is two carbons in this molecule. This is the same molecule that you see written in your booklet for Unit 2 that they're talking about, which is this molecule over here, CH3COOH. So this is CH3COOH. So this is called acetic acid. Now, the systematic way to name this is to name how many carbons you have in the longest chain, 1, 2 carbons, so that's F. So it goes meth for 1 carbon, eth for 2 carbons, 3 carbons is prop, 4 is bute, 5 is pent, etc. So you definitely need to know how to name compounds. And it's oic acid because this is a carboxylic acid. And carboxylic acids are the most famous of all organic acids. And the reason why they are so famous is because among organic acids, they are among the strongest organic acids. However, acetic acid is in vinegar. In fact, vinegar is made of mostly water, and then the next component in vinegar is ethanoic or acetic acid. And so, obviously, acetic acid is a weak acid because you do not drink sulfuric acid. You don't drink hydrochloric acid, but you do have a little vinegar on your salad. So obviously it's not a strong acid. So these are weak acids. However, in organic chemistry, they're important because they're the strongest. They're among the strongest of the organic acids. So my question to you: why is a carboxylic acid, for example, 10 to the 10 times more acidic Did you hear that right? Did you hear it right? 10 to the 10 times. 10 to the power of 10. That's 1,000 times more acidic than a comparable alcohol. Why? When they have a similar arrangement. Why are they so much more acidic than a comparable alcohol? Yes, I suppose saying yes, resonance is the best answer. Yes, I did see that someone said sharing electrons, and that is a little true because resonance is a delocalization of electrons, so they are being shared. But resonance is definitely the most important, term, and this is why I showed you the carboxylate anion. So here's the idea. The idea is this. When this is the acid, this is the acetic acid. When it releases its proton, it creates a carboxylate anion. Here is the carboxylate anion. The carboxylate anion can engage in two resonance forms, meaning there is no reason, because this is an oxygen and this is an oxygen, this is a carbon, there is no reason to say why this should be a single bond and why it couldn't just be the double bond. There is no reason to say the vice versa for the other one, because these are identical atoms. And in fact, if you were to take the carboxylate anion and try to do an experiment to find out how many double bonds are there in the carboxylate anion and how many single bonds there are, you might be surprised to find out there are 0. There are no single bonds and there are no double bonds, despite the fact that we draw it this way. And the reason is because these electrons are delocalized. And the reality is somewhere in between, where the electrons are moving up and down in this system, so that really each bond acts as if it's a bond and a half. So this acts as if it's a bond and a half, and these ones, because they have to be equal. This idea of resonance, where electrons are delocalized, helps to stabilize molecules. And that's why this is acidic, is for that reason. That's the main reason that they talk about. Now, could someone tell me that acetate anion? Look at the acetate anion. So you're looking at the chemical formula that they gave you, and the acetate anion is on the right side. What is the relationship between the acetate anion and acetic acid? This is a common type of, they wouldn't word it this way, but what I'm seeking is something that commonly comes up on the exam. Yes, it is the conjugate base. So the acetate anion, because it released a proton, it is the conjugate base of acetic acid. And H3O plus is called what? H3O plus would be called H3O plus, which is clearly acid. By the way, you can write H3O plus just as H plus. Okay, for those of you who haven't done it, the hydronium ion, yes, or the hydronium cation can be written just as H plus. And H plus would be called the conjugate acid, and therefore water is the conjugate base. Not something that you hear very often, but they would love to ask you a question like that, so that you notice that water is the conjugate base in this particular equation. Not always in this particular equation. So now I want to deal with the issue of Ka. Ka is the acid dissociation constant. A constant in chemistry, the equilibrium constants, means the product of the product over the product of the reactants. Now, the first thing I did was to forget about water, because water is in such huge quantity in solution compared to anything else that we are permitted to remove water as long as you do it from both sides of the equation. So I've removed H2O with the L, the liquid water, on the left side, and I was left with, if you subtract H2O from H3O plus, you're left with H plus. So that's the acid. So that's a simplification of the equation. And so then I'm going to use the equilibrium constant. And the equilibrium constant is the product of the product over the product of the reactants. Yes, exactly. So the product of the products is the acetate anion here and the acid H plus divided by the reactant. We only have one, which is the acetic acid. And of course, in stoichiometry, as long as everything's balanced, we're okay. We don't have to worry about anything. And then these things are raised to the power of their stoichiometric coefficient. So if there was a 3, in front of the acetate anion, then this would be cubed. It would be raised to the power of 3. And the last thing to mention is that these square brackets represent concentration in moles per liter. Okay, so that's the concentration. Okay, so that's Ka. So now you also need to know what pKa is. Now, P means negative log. It's just that simple. So every time you see P in general chemistry, it's a little different than amniotic fluid. It means a negative log. For example, you've heard of pH. pH means negative log H, negative log hydrogen ion concentration. pKa means negative log of Ka. pKb is negative log Kb. pKw is negative log Kw, etc., etc. So it's just negative log. So now the consequence of this is the source of many exam questions. And the consequence is this, and that is that as Ka goes up, as Ka goes higher and higher, because pKa is negative log, because it has this negative symbol, pKa goes lower and lower. So as Ka goes up, which is the acid dissociation constant, Ka, as opposed to the base dissociation constant, Kb. So as Ka goes up, pKa goes down. As Ka goes down, pKa goes up. And yes, they have an inverse relationship in that sense. It's not exactly inverse because it's inverse and it's a logarithmic, association. But the logarithm does not make it inverse. Logarithm just means that whatever you're taking the log of, it's just not going to go up so fast. So if you have something that's going up exponentially, you take the log of it, and now you have a straight line. So it's going up not so fast. That is the purpose of using the logarithm. Okay, so now we have this opposite thing in our minds as we talk about acid strength, because Ka is going to give you an indication as to the strength of the acid. Why? Because it's telling you how much product is being made. If you have more and more product, more and more acid being made, then Ka is going to be higher and higher. So if you have, if you look at HCl or H2SO4, sulfuric acid, their Ka values are insane. It's just crazy. It's like infinity. It's very, very high. So, and that's because they make so much product compared to the reactant. But when you look at something like acetic acid, it's going to have a relatively, it's not going to have the lowest Ka in the world, but it's going to have a relatively low Ka. It's a weak acid. It'll be something like 10 to the minus 5, which is 0.00001. So it's low a Ka value. So that means its pKa will be relatively higher than, for example, sulfuric acid or hydrochloric acid. And yes, Kb would be an indicator of basicity. So the higher the Kb, it would be the stronger the base. Okay, and okay, I don't want to confuse you or anything, but there are certain expressions that you should know. For example, if you have an acid which has a high Ka value, then I'm sorry, if you have a strong acid, then you would expect that its conjugate base will be weak. Okay, so think about that. You have a strong acid, the conjugate base will be weak. If you have a weak acid, you expect the conjugate base to be strong. So that's another thing that they like to play with. Okay, question number 6. based on the pKa values. So now we have a concept here, and the concept here is high Ka means low pKa. So high Ka, strong acid, low pKa. So we look at the list, and right away on your answer document, you would write with the lowest pKa value, 2.7, you would write right next to it strongest acid. Right next to it, you would write strongest acid. And with the highest pKa value, right next to it, you would write weakest acid. And this will give you some orientation. Now, we're going to deal with that fluorine thing, okay? Because we know it's the strongest acid based on the pKa value that they gave us. But in a minute, we're going to see why it's the strongest acid. We're going to go through the logic of why it's the strongest acid. But let's just answer this question to begin with. So now the question is, which of the following species is the strongest base? So the weakest acid is going to have the strongest conjugate base. So the base of that acid. Now you should never get confused about what the acid is and what the base is. And yes, the answer is D. Because you have to just try to remember the acid is defined as a proton donor. So this is an acid because it has an extra H plus here, extra hydrogen, so it can donate that, and therefore it goes according to the Arrhenius or Bronsted-Lowry definition of an acid. Yes, there's another definition of an acid which is not relevant here, and they would give that to you on the exam, which is a Lewis acid. They would explain it to you first, though, because it's not a traditional question. So you are expected to know that an acid is a proton donor, and this is a proton donor, and therefore this is the conjugate acid. This is the conjugate base of this acid because it is lacking a proton, but it could potentially accept a proton. And the definition of the base is that it can accept protons. So this is the conjugate base of this acid, and because this is the weakest acid, it has the strongest conjugate base, and so the answer for 6 is D. Now for 7, in which of the following pairs is acid strength correctly predicted? So there are a couple of issues here. One is one I would like to share with you. When I was in undergrad, I would memorize Brazenkopf, and sometimes this is helpful during some ACER practice questions. You know, you should have an idea of where the first 20 elements in the periodic table are, because during the real GAMSAT they've never provided a periodic table, and so I did not tell you memorize the periodic table. I wouldn't say that. I would say you should have a sense of it. And in the top right portion of the periodic table, I'm going to do this very poorly, but I will give you an idea of what I mean by Brazenkopf. So Brazen is this, and then Klopf is CL, and here's O. And so these often come up when it comes to electronegativity and the periodic table. And the periodic table, if you look in the top right corner, you'll see these elements. And these elements, and it is such that as you go up in the periodic table and to the right in the periodic table, electronegativity increases. And electronegativity means when you put these atoms in a molecular environment, they pull on electrons. They pull towards themselves. That's what electronegativity means. And so this is increasing electronegativity. So oxygen, for example, is more electronegative than carbon, because as you see, it is to the right on the periodic table. And so we would say that carbon will become a little bit positive, which is a symbol delta positive, a little bit positive, because oxygen is pulling on electrons, and oxygen is a little bit negative, delta negative, because it is pulling on electrons away from the carbon. So that's electronegativity. Okay, so that's the degree of electronegativity. So as you can see, that fluorine is the most electronegative element on the periodic table, and that's why it comes up relatively frequently on exams and should alert you immediately. Okay, so, and because it's there, we sort of need to deal with that fluorine and imagine what happens when fluorine is there. So I'm going to put fluorine over here. I'm just going to add a fluorine to this molecule here. And so then we're going to talk about what happens to the acid strength of this molecule. Okay, so when fluorine is attached to this carbon right here, because there's a carbon here, please remember, it's at the end of a geometric figure. So there's a carbon there. When fluorine is attached to it, being the most electronegative element in the periodic table, what happens to the carbon? It becomes partially positive because electrons are being withdrawn from it. And the fluorine, being the most electronegative element in the periodic table, becomes partially negative. Now, I have a question for you. What do you think about the stability of this neutral molecule? This neutral molecule, what do you think about the stability of it when you have a delta positive carbon attached to a delta positive carbon? Would you say that this molecule in its neutral form is stable? It's a yes or no question. No, it's not stable. This neutral molecule is not stable because there's two delta positive carbons that are connected. Now, how could this molecule possibly find a way to increase its stability? What could it do when it has these two delta positive things sitting right next to each other? The molecule can release a proton. By releasing the proton, it becomes negative. The negative charge engages in resonance, goes up and down like this, and it helps to put out the fire on this delta positive carbon. Yes, Stephen said it better than I. He said ditch the hydrogen. So that by doing that, you have the carboxylate anion being produced, puts down the fire on this delta positive. Obviously, if you put an extra fluorine on this carbon, you have two fluorines on the carbon, two electronegative atoms, both of them withdrawing from this carbon, making it hyped up, even more delta positive, making the neutral form even more unstable, making it more likely to reduce this. And then you can not only put out the fire of this delta positive carbon, but by having this carbon withdrawing electrons to itself because of the fluorine, it helps to stabilize the carboxylate anion. It helps to stabilize these electrons because fluorine is so electronegative. It's pulling, it wants electrons. This is even more stabilized. So by stabilizing the conjugate base, it increases the acidity. Answer is B. Because having that extra fluorine, it's twice as wonderful in terms of having the electronegativity. Just some quick mention. I'll just quickly, because we have to continue. Answer A is no good. First of all, alkyl groups, this is an expression you should memorize. Alkyl groups are somewhat electron donating. Somewhat electron donating. I didn't say very electron donating, just somewhat. And so that's a good thing to remember. And so if you have an ethyl group, okay, like ethyl alcohol or ethanol, I'm sure you would have some last night after school's finished. And when you have that, it is a little bit more electron donating, and so and we're comparing the alcohol with the carboxylic acid, and I've said already that the carboxylic acids are 10 to the 10 times more acidic than a comparable alcohol. And it's because of this resonance. The alcohol cannot engage in resonance. So, and then answer choice C, we're comparing having an ethyl group and an methyl group attached to the carboxylic acid group, and alkyl groups are somewhat electron donating, and of course we want an electron withdrawing group to make the acid stronger. Electron withdrawing, just like this group here makes the acid stronger. Then D, what's the difference there? Look at the location of the iodine. Iodine is down here on the periodic table. It's still an electronegative group, and but you have one in which the iodine is closer, and one in which the iodine is further from the carboxyl group. But clearly, if you have the electronegative atom attached as closely as possible to the carboxyl group, then it has a greater effect than if you attach it to a carbon downstream, further away. The effect will lessen and lessen and lessen. Okay, so yes, the ethyl group is somewhat more electron donating than the ethyl group. And I'll just say one last thing about this. What is this position called? This carbon. This carbon, what position is it called? There's a special word for it. Because this is carbon 1, because carbon 1 is the most important carbon. It has the carbonyl group attached, but this carbon is called the alpha carbon. Yes, the alpha carbon is carbon 2, believe it or not, and it is the carbon adjacent to the carbonyl carbon. And then, of course, there's carbon 3, which would be the beta carbon, and then so on, beta, gamma, etc. Okay, so question number 8. This is about SP. I'm sorry. About S character. And now S character is an issue that does come up regularly on the exam, believe it or not. And I'm not sure why. I think it's perhaps because it's not discussed a lot in undergrad. But S character is very, very simple. Look, you have an sp3. And an sp3 means that you have one s orbital and you have 3 p orbitals. So what's the s character of this? Well, 1 out of the 4 orbitals is s. So we have 25% s. So that's the s character. And sp2 is has 3 orbitals. It has 1 s orbital and it has 2 p orbitals. And so that means 1 of the 3 orbitals is s. So let's say that that's 33%. And of course, I'm just giving you round numbers just to give you a general idea of the process because ACER's not telling you. So, and then there's SP, which is clearly 50%. So now we know right away what has the most S character. Of these different orbitals, SP has the most S character. Now, what you can also hopefully you remember, if not, of course you're going to go through this in your review. You may remember that sp3 hybrid is for a carbon which is in the center of a tetrahedron. That's the shape. It has normal tetrahedral angles, 109.5 degrees, which is normal for the tetrahedron. A tetrahedron is sort of shaped like a pyramid with a triangle at the base and then an atom at the top and a carbon in the center of the pyramid. And so that is an sp3 hybrid. Then you have sp2, which is a flat triangle, trigonal planar. So a flat triangle where you have the carbon in the center of the triangle, and at each corners of the triangle you have another atom. That's sp2. And then there's sp, which means linear. And so that's a straight line, and that is composed of triple bonds when it comes to carbon, and sp2 double bonds when it comes to carbon, and sp3 single bonds. So when you look at the molecules that are provided, Roman numeral 1, those are single bonds, so that represents an sp3 hybrid. And Roman numeral 2 has double bonds, so that means trigonal planar sp2 hybrid. And Roman numeral 3 is single bond sp. So that means, well, we're told that increasing S character means increasing electronegativity, and we already know that increasing electronegativity means increasing acidity. So the one with the highest S character is the SP, which is linear, and because it has the highest S character, it's going to be the strongest acid, then 2, then 1. So the answer would be D. So if you wanted to, if you have the gold standard book and you wanted to read up on sections that are relevant, the new sections, Chem 6.1, 6.7, 6.8, and for carboxylic acids is Organic Chapter 8.